Thanks for the kind introduction and the opportunity to present. So today I will briefly introduce my recent work regarding quality assurance of biomedical ontologies. So the overall eventual goal will be ultimately enhance the biomedical data science applications. So as many of you have already known, in biomedicine, there has been a lot of ontologies or terminologies created due to different needs, including SNOMED CT for clinical terminology, gene ontology for genome annotation, and FMA for modeling the human anatomy. So ontology has played important roles, serving as knowledge source for many applications in biomedicine, like data annotation, knowledge management, and data integration, NLP, or supporting clinical decisions. So the quality of the biomedical ontologies will directly impact all the downstream medical applications. So here I'm just briefly showing an example how a missing is a link in the semantic hierarchy will affect the, for example, searching for a cohort. For example, here, if there's a missing link, so this means a missing subtype for carcinoma of larynx. Then when we search for the cohort of carcinoma of larynx, then this subtype, the patient with this subtype will be missed. In terms of like information retrieval, means that the recall is decreased. And it's also affecting all the downstream analysis, whatever analysis you want to use to do the analysis. So given the important roles, ontology plays, we must ensure the quality of the, ontologies are top rate. However, due to the, growing size of the large terminologies and also the structural complexity, for example, in addition to the ESA hierarchy, as Oliver has showed for, in the vaccine ontology, they have, the definition will not only include ESA relation, but some other, associative attributes and the relations well defined. So due to this kind of structural complexity and growing size of the concepts, for example, the SNOMED CT has over 330,000 concepts right now. So it's like, auditing the ontologies or finding or debugging the ontologies is like finding needles in a haystack. Sometimes you cannot do it manually, because of the large size. So one of my research interests recently has been developing computational methods to auditing the ESA hierarchy of biomedical ontologies. For example, for detecting potentially missing ESA relations or incorrect relations or some missing concepts. So today I'm going to only focus on missing ESA relations. The current technology gap for this kind of auditing techniques is most existing methods, they only identify problematic areas. So for example, they may give you a subgraph or some kind of a subnetwork so that the ontology curator or editors can look into, but they have to manually look into the structure and find out what's the exact quality issues and how to fix them. So this process is still very time consuming and labor intensive. So for the work my group has been doing is we try to develop automatic ways to not only identify problematic areas, but also detect the exact quality issues and make automatic suggestions so that the ontology curator or domain expert can directly just say yes, no, instead of coming up with the solutions by themselves. And next, I will focus on introducing two methods we have been developing. The first one is non-lattice based auditing. So for those who are not familiar with non-lattice, first I'll just give you a very brief background about. So lattice is basically a desired property for ontology in terms of either hierarchy. So basically, for those large ontologies, they have, normally it's not a tree structure, it's a DAG structure, means that a concept or a node may have multiple parents. So the non-lattice means like for any given two concepts, they have maybe more than one, at least two maximal common descendants. So for example, in this example, if you take a look at node 1 and 2, they have two maximal common descendants, 5 and 6. So that means the 1 and 2 are a non-lattice pair. And we do a reverse computing of the minimal common ancestors of this 5 and 6, then we obtain a non-lattice subgraph given a non-lattice pair. So this way, it's more kind of a closed computation, and it's like smaller size subgraph we can further look into to identify potential quality issues. So for, you may think that computing this kind of non-lattice graph may be time consuming. And we did develop a very efficient algorithms using dynamic programming to actually compute those non-lattice subgraphs, even within the largest terminology SNOMED CT very efficiently. And so then that solves our computational problems to get all this kind of substructures for the analysis. Then, based on those substructures, subgraphs we have computed, then the next step would be how we, using sort of lexical attributes of the nodes or concepts, to come up with the solutions to fix the quality issues. So in the left-hand side, you will see, what you see is a non-lattice subgraph in SNOMED CT under clinical finding hierarchy. So if you take a look at node 5 and 4, even if you are not a domain expert, probably you can already infer that congenital sacral meningeal cell is already a subtype of congenital meningeal cell. So that's why we used the lexical attribute to infer this kind of potential missing is. Well, in this example, we can also infer another one from number 6 to 4 in terms of lexical attributes. So if you see, cervical spinal hydromeningeal cell is meningeal cell, and it's also congenital. So it should be a congenital meningeal cell. So I'm just giving you an example, like how we can leverage certain lexical attributes to do this kind of detection. So in this example, the result would be we have two potential missing is the relations identified. Then we can directly hand over to the ontology curator or editor to directly verify if these are valid or not. So this is an example in SNOMED CT. And here it shows another example in the biological process under gene ontology. So similarly, we got the non-lattice subgraphs first, and then we do a kind of lexical analysis to make the prediction. So here you see that's another link here, because astral, according to the current structure, astral microtubule depolarization is set on plastic, so it should be, there's a missing link here. but still, again, it needs domain experts, the final validation to be able to put this kind of suggestions into the gene ontology. And here it shows an example in the NCI Thesaurus, in the drug, food, chemical, or biomedical material subhierarchy. For this one, what we may suggest is missing is, but actually it's actually the 3 and 4 are kind of synonyms which can be combined into a single node for this kind of drug instance. So I'm just showing you an example without, bothering with the technical details. But if you are interested, we can talk about that offline. And we have done a lot of, this kind of lexical analysis based on non-lattice graphs to make the auditing, the different kinds of biomedical ontologies. So as you may already think, due to the large size, we may have a lot of non-lattice graph obtained. And there may be some structural similarities among different subgraphs. Then we sort of trying to group certain similar graphs together, then we can avoid redundant analysis. So for this example, if you take a look at the left-hand side, it's a substructure and the suggested remediation. That means we have a suggestion for missing ISA here. Similar structure on the right-hand side, but if you take a look at into the details of the concept names, the only difference between the left and the right is negative versus positive. So for this kind of similar substructures, we don't need to actually go evaluate each one of them. So we try to minimize the manual labor. So we try to group this kind of similar substructure together. And what we did here was we're using the graph isomorphism to actually find the similar graph structure purely from the structure node-wise. And then we use the Doc2Vac to learn the representations for concept labels for each node. Then we use the, compute the similarity scores to find the similar substructures. So this is more kind of using those embeddings to help with the quality assurance of the ontologies. Then next, I will introduce a more recent work published this year, still kind of using both structural and also lexical information. But this work does not require us to focus on those substructures like non-lattice subgraph. This work is more kind of more exhaustive, applied to the whole version, those of ontologies, but without need to get into the detailed substructure. So this one, it has 3 main, this framework has 3 kind of components. So first we represent our model concepts in a sequence, and then we have defined some algebraic operations to model the potential interactions between the concepts. And then we have inference rules defined for predicting potential missing ISA relations. So I'm just going briefly showing by examples to see, what's the basic idea. So for each concept, we model it as a sequence of primitive elements. So primitive element can be a single word or a subconcept. So here, subconcept, we mean that if the term, for example, here we are focusing on the gene ontology. If a geo term has another geo term embedded in the concept or in the term, we call that embedded concept as subconcepts. And a single concept may have multiple representations as shown in this table. And we also have the taggings, including the part of speaking tagging and also the subconcept tagging to make the sequence-based annotation. And then we define those algebraic operations. For example, here we focus on define intersection operation. This will realize the computational of the subsumption-based longest common substance. So this way we can calculate intersection based on the sequence of those primitive elements. So for example, if we intersect two concepts, one is protein catabolic process, the other is cellular protein metabolic process. So if we intersect these two, what we obtain is cellular protein catabolic process. Basically, it gets to a more specific meaning of the concepts. And then we have different rules defined to try to predict or detect potential missing is, so basically the monotonicity rule, what we are thinking was like if the element wise, if the corresponding element has the subsumption relations, then we may infer that the overall concepts may have subsumption relation as well. And for the intersection rule, it's more like if A is more specific than B and A is more specific than C, and there is another concept which is B intersects C, then we say that A is also a B intersects C. So that's kind of inference. And for subconcept rules, it means that if a subconcept appears at the end and there are some conditions satisfied for the front element, so we sort of make a prediction they may have a subtype relation. And we applied this inference framework to one version in the 2018 of the GE Ontology. And in total, over 1,900 relations were detected as potential missing ISA. And we randomly selected 210 for domain expert evaluation. As you see, the valid missing is we have the rate, different kinds of rates for those precisions. But overall, this is already, although you see it's around like kind of a 60 or 50, but in terms of the GE Ontology, this rate is already pretty good, because the terms in GE Ontology is more complicated than terms in the SNOMED CT. So those are all validated by our domain experts. Here we are showing some examples obtained by different inference rules. For example, the first one obtained by the monotonicity rule is the cellular response to ketone, is the cellular response to organic substance. And we also have the incorrect or erroneous missing is detected. But because we are automatically suggesting missing is, so this kind of incorrect is has to be validated, by the domain expert based on what we leveraged to make the prediction. So currently the missing is automatic per suggestion, but erroneous one needs a bit more effort from the domain expert to further validate those existing relations that are leveraged to make the predictions. And we also have additional, work regarding the auditing ontologies. So for example, we have recently have a transformation-based method, also kind of a lexical and structural combined hybrid approach to detect missing issues in the unified medical language system. And also we have experiments, different kinds of learning approaches to validate those predicted missing ISA and also predicting the concept names for missing concepts. So in summary, as we already seen, so our general approach is basically relies on the hierarchical ether relations and the attributes of the concepts. So it's generally applicable to, apply to other ontologies, including drug-related ones, such as Axonome. And in the future work, we intend to investigating more learning-based approach to detecting missing ether, and also to identify incorrect ether as well. And also, the last but not the least, we wanted to find the root cause of the hierarchical quality issues. So this one means that some of them will not be directly adding those missing ether into the ontology, like what we did in the most of the ontologies, but we will have a more systematic way to find those potential other root causes, like in the other defined associative attributes or relations, to see if those root causes will be can be identified to further enhance the qualities. So last, I would like to thank my funding support from both NIH and NSF, and my collaborators at UT Health, University of Kentucky, before I joined UT Health, and also, Dr. Oliver Goldenreader at NLM, and my team members, Rashmi and the Fongbo, for their excellent work. So that's it. Thank you so much for your attention, and I would be happy to take any questions.
Thank you, Licong, for an excellent talk. Anyone has any questions for Licong? And if you have any question, I mean, during the talk, you can also, use the chat so that, we can go over after talk.
Yes, good one. I can ask the first question. So I think it basically automatically detects possible errors or missing values. It's a very nice feature of your program. So one question is, like in ontology development, we have something called, asserted is a hierarchy, right? And then inferred is a hierarchy.
Right.
And some ontologies, they put only asserted hierarchy there. So they did not put the inferred hierarchy there. And some ontology definitely they put also the inferred merged version there. So I don't know, when you do the testing, have you look at whether or not, like for example, gene ontology, it's already after inferred hierarchy generation, or it's just that you took it, whatever it is, it may just be asserted version. Yeah.
So yeah, you are right. So basically, ideally, each ontology, and some of them, they did release two versions. One is this asserted or stated version, and another is the inferred version. So basically, getting back to the theory side, it's more about most of them are modeled using all, the description logic. So basically, when they create the ontology, it's more all stated or asserted. But when they release the version, the DL classifier will automatically infer those, is the relations. For example, for SNOMED CT, we can parse the the released file to get the asserted version. So we will have both asserted version and the inferred version. But so for the methods I have presented, where the analysis are all based on the inferred version. So we directly, using the inferred version to perform the auditing. But when getting back to fix them, like for example, if we have a missing is identified, so first the ontology curator needs to see if this is valid or not. So if it's valid, so it is the simple solution would be directly add that into the stated ether. However, for some cases, it may not be that simple. That's why, so then in the future work, we would like to get back to the root cause. Basically, that means that it may involve just fix some of the definitions in the associated relations instead of directly adding the ether. So this way, the missing ether can be automatically inferred through the DL classifier by, including some other association relations that may be missing or incorrect. So
Great. Yeah,
did I answer
that's
the
good.
question?
Yeah.
Or I should have more clarifications?
Yes, good. Thank you.
Thanks for the question.
Any other questions from the audience?
Yeah, Licong, this is a very, I think it's a very good work.
Thanks.
And I want to ask you the future development. Are you going to only focusing on the 3 ontologies that you are in your presentation? And have you ever thought actually you can use this method to develop ontology out from a big list of terminologies?
So basically, you mean that develop a completely new ontology or auditing other new ontology?
Yeah, computing new, because I know there is a lot of terminologies out there. They do not have is a relationship among them, and people do not have time to build them. But it's obvious to see there is a relationship just from the terms.
Yeah, that's a very good suggestion, actually. So for those ontologies, without a very good quality, semantic is a hierarchy, I think some of our methods can, for example, what I have showed you, some lexical-based analysis can be used for, help with organization of the hierarchy. And also the learning-based method can also help as well. So basically, we learn embeddings from different sources and make predictions to, better structure those ontologies which do not have a good quality of ether. So I think this is a very good suggestion. Thanks.
Yeah, and also in the future, I don't know if you approach people in GO, if you have the high you got a high score of your prediction, I suggest that you will need to reach out to GO, give them your suggestion.
So for your information, the GO suggestion is under we are under the final review of those, because GO has released very frequently. So we're just because some of them as like further validation, they have been already fixed. So we are planning to submit those suggestions, but without any duplications, because some of them are already fixed. So we only want to submit those which are still currently not fixed. So that's in process. And but for the NCI Thesaurus, we did for our published work, we did work with the expert from the NCI Enterprise, the EVS service. So actually, when they review our results, they directly make the fix directly into the NCI Thesaurus. And some of them are already corrected and also already in the production right now. So we are very successful for the NCI Thesaurus, but for G ontology, we're still in the process of making these suggestions more kind of avoiding those already fixed, and to submit to their open like forums for them to further review and fix.
Right. What about SNOMED?
SNOMED CT is actually a totally different story.
I'm sorry, but can I interrupt you? I think in the interest of time, I think we have to move on. I'm sorry, so we can continue the discussion after the workshop. I do have a couple of other questions, but let's move on. And thank you again very much for an excellent talk.